Okay, year 11. New chapter, talking about galvanic cells and also these things called standard electrode potentials or standard reduction potentials. Okay, we've still got this inquiry question is the word I'm looking for. How is the reactivity of different metals predicted? Okay, so we learnt a little bit last chapter about activity series and predicting the reactivity of metals with metals. Some of them liked electrons more than others. So some of them as ions can steal electrons from other solid metals, and you can get displacement reactions. So I thought I'd start this chapter with a little revision on that. Okay. So we know we get displacement reactions in circumstances where we have one metal in contact with an ion of another metal, where that ion has stronger attraction to the electrons. So for example here, I've got metal 1 and metal 2. Metal 1 is just as a solid metal. Metal 2 is as an ion, 3+. And here in this case we get a reaction happening where the electrons jump over to metal 2, because metal 2 likes electrons and attracts electrons more than metal 1. Okay, the other way we can say it is metal 1 is more reactive than metal 2. Metal 2 is more stable than metal 1. Okay, I'm contrasting it here with another metal, metal 3. Metal 3 is an ion. Metal 1 has these valence electrons, but metal 3 doesn't have a strong enough attraction to attract them away. Okay, so metal 1 is more stable than metal 3, or metal 3 is more reactive, so it stays as its ions. Okay, so electrons are transferred, and then the ion metal, so like our metal 2, precipitates out as a solid metal, whereas this metal 1 dissolves into the solution. Okay. How do we know the relative differences between how metals attract electrons? We had the activity series. We're going to formalize it a bit more. Okay, so we had this metal reactivity series. We had our most reactive up here and our least reactive down here. Our most reactive weakly holds on to and attracts electrons. Okay, and we've got stuff like group 1 metals here, like potassium, sodium, and lithium, that we know have one valence electrons, and they become much more stable as the ion of the 1+ ion, where the outer shell is complete. And down this other end, we've got these least reactive metals that strongly hold on to and attract electrons. They like to be just the solid metals and not the ions. So stuff like copper, silver, platinum, and gold. These are the least reactive. So this activity series gives us a ranking of how reactive metals are. Potassium up one end, gold down the other. Okay, very unreactive. So remember, activity is a relative measure of how easily a metal is oxidized. Okay, so the most reactive, they're easily oxidized. The least reactive, very hard to oxidize. Very hard to oxidize gold. Okay, for example, we saw that when copper metal was placed into a silver solution, or silver plus ions, a reaction occurred to displacement reactions where the copper solid lost its electrons to silver, okay, and became copper 2+. It went into solution, so it would have turned blue, and we had silver precipitate out. So you would see kind of like some dark metal covering what was the copper. Okay, we also saw from the examples last chapter that when you put iron and copper ions in presence, you will get a displacement reaction where iron is oxidized to iron 2+, it goes into solution, and copper is reduced to copper 0 and precipitates out as that distinctive copper orange-brown color. So in general, ions that are less reactive will take electrons from metals that are most reactive. So ions further to the right will take electrons from metals further to the left. Okay, so here's some examples. Magnesium metal placed in a solution of zinc 2+. Well, zinc is further to the right. Zinc will take those electrons from that magnesium metal. Zinc placed in copper. Copper's further down here. So copper will take those electrons from zinc. Tin metal placed in a silver solution. Silver's all the way down here. Tin up here. electrons will transfer. So electrons will transfer down to the least reactive one. Okay, but have to remember the other way. These reactions won't happen. Okay, let me just erase those. Aluminium metal up here placed in a calcium 2 plus solution up here. Well, aluminium likes its electrons more than calcium. It's not going to give them away, so no reaction occurs. Tin, there we go, SN for Stanum. Tin placed in a magnesium 2 plus solution. Magnesium's all the way up there. The tin electrons are not going to, well, the tin's not going to let go of those electrons and transfer them up there. No. And silver placed in a lead solution. In a lead solution, well, silver already likes its electrons too much. It's going to hold on to them. You're not going to get a reaction. They're not going to want to go to lead. All right. So let's use our predictive powers to find which of these combinations will result in a displacement reaction. So number one, we've got barium and iron 2 plus. Barium's all the way up the top. Iron 2 plus is down here. Iron likes electrons more than barium, so electrons are going to transfer. Tick, we will get a displacement reaction. Okay. Silver and H plus. Silver likes electrons. It's more further to the right here. Electrons will travel from... Oh, hang on. I've got it around the wrong way. Okay, so electrons will not go over to the H plus. So no reaction. Okay. Okay, magnesium and magnesium 2 plus. No, you won't get a reaction between the same metal in solution as you dip it in. Okay. Zinc and aluminium. Maybe I need to clean this up a bit. So we've got zinc up here and aluminium up here. So out of the two, zinc likes its electrons more. Okay. Zinc has already got all of its electrons, so no reaction. Zinc and lead, or lead's down here, zinc's up there. Lead likes its electrons more than zinc. Lead hasn't got all of its electrons. Electrons will transfer. We'll get a displacement reaction. Silver. Gold. Terrible. Gold and potassium plus. Ooh, extremes. Gold likes its electrons more. It's already got all of its electrons. Yeah. So no reaction. Silver and platinum. Alright, we're dealing with down here. So out of the two, platinum likes its electrons more. Platinum's an ion. It will take the electrons from the silver. So we will get a reaction. Hydrogen and zinc. Alright, hydrogen's further to the left. Hydrogen likes its electrons more. It's all full. Okay, zinc's further up. No reaction. Okay. Here's a bit of revision as well. A full redox equation for the redox reaction between barium and iron 2 plus. Well, barium's here. Iron 2 plus is here. Iron is more stable. Here it is as an ion, so barium will transfer electrons to that way. So we will get a displacement reaction here. So, two half equations. Barium is going to barium 2 plus. And to balance it out, we need the 2 electrons on that side. Okay, iron 2 plus is going to take those electrons, put them on the left-hand side, and we're going to iron solid. So we're going to precipitate out the iron. Okay, we've got 2 electrons being given and 2 electrons being consumed. We can add these together without multiplying them. So barium solid plus iron 2 plus, 2 electrons on each side. Let's not bother writing them down. Barium 2 plus aqueous plus our iron solid. Alright, next problem. Example 3. Give a full redox equation for the reaction between zinc and lead. So zinc solid and lead ion. Zinc's up here, lead's down here. Lead likes electrons more than zinc. Lead is an ion, so it's going to transfer electrons down that way. Okay, so we're going to get a displacement reaction. Zinc half equation. Zinc solid is going to zinc 2 plus. 2 plus because that's the only ion that zinc will form. That's the only oxidation state. So we need to balance it with 2 electrons. And our lead 4 plus, oops, sorry guys. Lead 4 plus is going to lead solid, so we need 4 electrons to do that. Alright, we haven't got the transfer of the same amount of electrons. We've got 2 and 4, 2 being produced, 4 being consumed, so we need to multiply that top one by 2 when we add them together. Alright, so when we add them together, we're getting 2 zinc solids, and moving down to the second one. We're leaving that by itself. Lead 4 plus, we're not multiplying it by any coefficient. And the 4 electrons, but I know they'll cancel. We're going to 2 zinc ions. And 4 electrons, cancelled out with the other side. Excuse me. And 1 lead solid. Alright, so there's my full redox equation. Next video we'll start looking at this table.